Today we're going to look at the force of gravity. The force of gravity is a force that is often credited to Isaac Newton. Newton's great discovery was that the force of gravity responsible for pulling an apple off of a tree to the earth is the same force that's responsible for planetary motions, or the motion of the moon around the earth. So what Newton did is he made gravity a universal force. It's a force that acts between all objects in the universe. So Newton found that the force of gravity depended upon the mass of the two objects, and it depended upon the distance between the two objects. So the force of gravity gets larger as you make the mass of one of your objects larger, or force gravity gets larger when you make the mass of the other object larger. So gravity depends on the product of the two masses. Gravity gets weaker when you make the distance larger. So the largest force of gravity will occur when your distances are close and your masses are large. When you're measuring distance, you measure from the center of one object to the center of the other. Notice that force of gravity is a great example of Newton's third law. So whatever force of gravity exists on the blue object will be the same as the force of gravity that exists on the red object. So if we make the mass of the blue object larger, both gravities get larger. Okay, it doesn't matter which one we call mass 1 and which one we call mass 2. Okay, so Newton's gravity can be summarized mathematically by saying the force of gravity is equal to the gravitational constant times mass 1 times mass 2 divided by the distance between the two objects squared. The value for the gravitational constant can be found on your reference sheet. It is approximately 6.67 e to the negative 11th. Okay, the force of gravity is responsible for things like free fall or any kind of vertical motion. So anytime you have vertical motion with gravity as the only force, you find the force of gravity between your two objects. You then use that force to figure out the acceleration of the object. On Earth, that acceleration will be equal to negative 9.8 meters per second each second. And then you use that with your motion equations. It's interesting to note that the mass of the object does not affect the acceleration of the object. So even though mass does affect the force, it does not affect the acceleration. So for instance, in this video I have a heavy shot put and a light field hockey ball, and when I drop the two, you'll notice that the two objects fall side by side. They both have exactly the same acceleration. We can see objects accelerating, so if you look at this video, these dots represent the position of an object that was falling every 1/30th of a second. You can see the dots start out really close together, and you can see the spacing becomes larger and larger, showing that the object is accelerating. Finally, for vertical motion, if you plot out the velocity of the object versus time for an object that you threw straight up in the air, you'd note that the object starts with a certain positive speed, meaning it's going up. That speed decreases as gravity slows it down. When the object reaches its highest point, it will have a velocity of 0. The velocity will then start to go into the negative numbers, meaning the object will be getting faster but moving downward. When the object reaches its original height, it will also get back to its original speed, but in the opposite direction. The slope of this graph should be negative 9.8 meters per second, and depending on the accuracy of your data collection, you should get pretty close to that value.